So we can switch points from polar coordinates to rectangular coordinates and rectangular coordinates to polar coordinates, but the coordinates of points aren't the only thing that depend on the coordinate system that you've chosen. Equations actually also depend on the coordinate system you've chosen. So for example, here's an equation, right? We know what this is. So 4 is the square of the radius for the circle. So this is a circle with radius 2. But it has x and y in it. And those are the rectangular coordinates for the points that this equation is describing. So it must be possible to somehow translate this equation into a polar description of the points that this is describing. So let's see if we can do that. Now over here I have the equations that we worked out for translating from rectangular coordinates to polar coordinates and back. And of course we're going to end up using these. So the equation that we're starting with here is x squared plus y squared equals 4. And somehow we have to use all of these to get an equation only with polar coordinates in it. So the idea here is to get rid of, when we're done, we want no x's and y's. We want only r's and thetas. Then we'll have successfully switched from a rectangular equation to a polar equation. For this particular polar equation, there's a really nice shortcut. X squared plus y squared, well that's the right-hand side of one of our translation equations down here. X squared plus y squared is just r squared. So r squared is 4. And then if you really want to, you could even take square roots on both sides. R is plus or minus 2. But as we've seen, every point that has an r coordinate of -2 has an alternate description where r is positive 2. So you don't even need the negative. You could just have the positive. So r equals 2. If you think about it, from what you know about circles, this particular equation makes perfect sense. Because if you draw a circle centered at the origin with radius 2, so something like this, right? Every point on this circle is 2 units from the origin. That's what makes the radius of the circle 2. And so every one of these points on this circle will have polar coordinates r equals 2, and theta is, well, something. What theta is depends on where you are around the circle, but all of the r coordinates on this circle are 2. And so every point along this circle satisfies the equation r equals 2 because the r coordinates are all 2. So this makes perfect sense. But even if you didn't notice this, so here I used a shortcut that was sort of special for this equation, but even if you didn't notice that there was this shortcut, you can still come up with the same equation. So x squared plus y squared equals 4. Right? We have other equations we could use, like these two. X is r cosine theta, and y is r sine theta. So we could just replace x with r cosine theta. And that's squared plus, and then we could replace y with r sine theta squared, and that's 4. Then you could multiply this all out in an attempt to simplify it. I hope you would attempt to simplify this. So you get r squared cosine squared theta plus r squared sine squared theta. And then I hope your experience with the Pythagorean identities would prompt you to want to factor out this r squared times cosine squared theta plus sine squared theta equals 4. And then in the side parentheses here, that's 1 because of the Pythagorean identity. And now we're back to r squared equals 4. So either way, whether you notice the shortcut or don't, you end up with the same equation in polar coordinates. All right, that worked pretty well. Let's try another example. Let's rewrite the equation x squared plus y squared equals x in polar coordinates. One way to go about this is just like before, replace x squared plus y squared with r squared. And then x, well, this time there's no shortcut with r squared, but remember x is just r cosine theta. So we can replace this with r cosine theta. And then as long as r isn't 0, we could divide both sides by 0 here. Or, I'm sorry, divide both sides by r. So this is if r isn't 0. And you get r equals cosine theta. The only question is, are we missing any points here by insisting that r not be 0? Well, the only point whose r coordinate is 0 is the origin, and for this equation, one description of the origin is 0, pi over 2, and that satisfies this equation. So the origin is described by this equation. So we actually haven't lost anything by insisting that r not be 0. Okay, but what is this? What is this equation describing? One way you could figure out what this equation is describing is by completing the square here. Because we have an x squared and a y squared, it seems like maybe this is a circle. So let's complete the square. Let's move this x to the other side. X squared minus x plus y squared equals 0. Now for our y coordinates, those are already, the square is already completed for our y coordinates. So let's complete the square for our x coordinates. Looks like to complete the square, remember the recipe is you take your linear coordinate, which is -1 here, divide that by 2, square that, so that's 1 over 4. So we'll add 1 over 4 to both sides. So x squared minus x plus 1 over 4 plus y squared equals 1 over 4. And now this part, x squared minus x plus 1 over 4, is a perfect square. That's x minus a half squared plus y squared equals 1 over 4. But 1 over 4 is the square of a half. So this looks like this is a circle whose center is at 1/2, 0, and the radius is 1/2. So that's like this. So this is r equals cosine theta. Okay. Let's try another example. So let's rewrite this equation, x equals y squared in polar coordinates. So no nice shortcuts involving this Pythagorean translation equation, so let's just use x equals r cosine theta and y equals r sine theta. So x is r cosine theta, y is r sine theta, squared. Seems like we should multiply out this squaring, so r cosine theta equals r squared sine squared theta. And then you could divide both sides by r, I guess. Get cosine theta equals r sine squared theta. And then at this point, well, at this point it's hard to know what else to do. It's hard to know if there's any sensible way to rearrange this equation that's going to actually illuminate anything about this, the collection of points that this equation is describing. You could, if you wanted to, divide both sides by sine squared, I guess, if you thought that would help. You'd get, I'm going to move the r to this side just because I want to. So r equals, so we have a cosine over a sine, that's cotangent theta. And then we have a 1 over a sine, and that's cosecant theta. So this parabola, x equals y squared, right, that's going to look something like this, is also given by this equation in polar coordinates. All of these examples so far have been going from rectangular coordinates to polar coordinates. Let's see how it would work going the other way. So let's write this equation in rectangular coordinates. R equals sine theta. Unlike going from rectangular coordinates to polar coordinates, right, there's no easy foolproof translation equations that will let us eliminate r and theta. Right? These first two equations, we could always use them to eliminate x and y and end up with r's and thetas, but there's no r equals equation that will let us eliminate r no matter what. So it's a little trickier. But there are some algebraic tricks we could use. Right? We see that there's a sine theta right here, and so it seems like probably that's going to have something to do with y, but to make it y, it should have an r with it. So let's multiply both sides by r here. Seems like a sensible thing to do. So on the left we have r squared, and on the right we have r sine theta. But r sine theta, that's y, and r squared, that's x squared plus y squared. Okay, that wasn't too bad. It turns out this is, if you do this completing the square trick, it turns out that this is a circle like this, centered at 1/2, or 0, 1/2, and with radius 1/2. All right, finally, let's look at this example. So r equals 1/2 minus cosine theta. This time it's quite tricky to know what to do. Because there's a cosine, it seems like probably we want to get that with an r somehow. We could multiply the numerator and denominator on the right by r, but also we could just clear the denominator, and that would multiply it by the r on the left. So let's take this equation, r equals 1/2 minus cosine theta. Let's multiply both sides by 2 minus cosine theta, just to clear the denominator on the right-hand side, so these simplify away. While we're at it, let's distribute this r. So we get 2r minus r cosine theta equals 1. This feels like a partial success at least, because r cosine theta, that's x. So now we have 2r equals, 2r minus x equals 1. So we have this r by itself. We've seen before that if we can get this r to be squared, then we could use our Pythagorean shortcut equation here. And I guess maybe if we have two ways we could make this r squared. One is just to multiply everything by r, but then we're going to have some other r's that aren't squared, so that doesn't seem so great. Another way we could get this r on the left-hand side to be squared is to get it by itself and then just square both sides. Let's try that. So add x to both sides to get the r, get all the rectangular coordinates away from the r. So we get 2r equals x plus 1. And then we could just square both sides, like this. So on the left, we're going to get 4r squared equals, let's not multiply out this squaring just yet. We might need to later, but it's not really clear. Okay, r squared is x squared plus y squared. It looks like we probably should multiply out this squaring because we'll get an x squared and we could combine it with that x squared. So let's multiply this out. X squared plus 2x plus 1. You distribute the 4 just so we can collect like terms. 4x squared plus 4y squared equals x squared plus 2x plus 1. And then, I don't know, move all the x's to the left, I guess. At least combine the x squared terms. So subtract x squared from both sides. 3x squared plus 4y squared equals 2x plus 1. Okay, so we did it. We converted this polar equation into a rectangular equation. I don't know that it really helped because at this point we don't really know what this is an equation of, although we will later in the quarter.